Okay, this is page 8 of the I.O. notes. This is take 2. Last time I didn't have my microphone plugged in, so maybe this will be even better. So I just wanted to kind of back up and point out that with polling, your program is actively engaging with the I.O. device, checking on its status, and then taking actions. With I.O., the idea is that your program, it will set up the I.O. device initially, enable it to interrupt the processor when it needs service, like when it's received data or it's ready to send more data or there's problems. And then your program just kind of goes off and does its main application. And then the data that's coming to and from this I.O. device will just show up in buffers and memory. And it works very nicely. It can let you get more done because you're not constantly waiting for I.O. Now, when an interrupt occurs or an exception occurs, there's a piece of hardware that's part of the processor called the interrupt controller. That's interrupt controller. On the ARM, it's the nested vectored interrupt controller, NVIC, but I'm just going to call it interrupt controller for now. And what it does is it chooses a handler, which is just a subroutine, to run in response to an exception. This is different than what we've seen before because normally in our program has control over which functions get called, and that's synchronous. What's happening now is you get this signal, say from an I.O. device, and the hardware says, okay, I'm going to pause the application and I'm going to run a subroutine. So it's the hardware that's invoking the subroutine. So that's something different than what we've seen before. So let's look at this as a diagram. So here's our application code. So I'm just going to show multiple lines here to indicate instructions being executed, and the control flow. The control flow is the name for the sequence of instructions as they are executed. So normally control flow is sequential, but sometimes you have branches and stuff like that. So that would all be part of this. You might be doing loops and whatever. And then let's say at this point in time, an exception is raised. So we're going to suspend the application, and it's the hardware that does this. So it saves any register contents, that kind of stuff that it needs, onto its stack, and then we go over and we run the exception handler, or the hardware runs it. So the exception handler is just a subroutine, just like any other one really. Usually they don't take any parameters and the return type is void because the hardware usually doesn't have parameters to pass it and doesn't care about a return value. And so the program flow continues this way. When the exception handler returns, we go back over here to the application code and it is going to get resumed wherever it left off, so at the next instruction. And what's kind of neat about this is the application code is unaware that it was suspended. So it's done in a seamless way, so none of its variables or a stack change, anything like that. So let's just write that down. The application is unaware of the interruption. So an example of an exception being raised would be an interrupt request from an I.O. device, and an example of an exception handler would be an interrupt service routine. So just a bit of terminology related to that. So a ISR equals interrupt service routine or subroutine, and it is it's the common name for exception handlers for IRQs. And ARM has their own name for these things. So ARM calls ISRs IRQ handler. We're going to see an example of this